saw about the series and parallel combination of resistors, but as I said, there are certain cases wherein the resistors are neither in series nor in parallel. Okay, so here in this example, we need to find the value of the equivalent resistance between the points A and B. Okay, now as we can observe here is that neither of the resistors are in series nor in parallel. Okay, but if we'll observe it carefully, we can see that there is symmetry about on this structure about this axis, about this plane. If you consider this. So about this axis, about this plane, we can see there is symmetry about the structure. There are two triangles and a horizontal. In the horizontal branch, there is some resistor. Okay. So what we can do here is that since there is symmetrical, so we can use a concept that we can introduce a ground plane in this, such that this can be considered as at zero potential. Okay. So when we will consider it as a connected it by some conductor, we can replace the other half. We can remove this other half and we can consider this as a ground plane, so that this point would be at zero potential. Okay. So what we will be doing later on is that first we will be finding out the resistance between the points A and C, and at the end we will be multiplying the result by 2. Since we are dividing it now into half, so at the end we will be multiplying the resistance by 2, so that we can get the equivalent resistors between 2 points A and B. Okay. So suppose what I'll do is now remove this other half of the structure, but before removing it, we can see here is that this plane divides this resistors into two halves. Okay, so the resistors will get divided into two values, R by 2 and R by 2, okay, which are in series with each other. Okay, so after introduction of this plane, after introduction of this axis, okay, you can remove the other half. Okay, so after removing the other half, we will be left with this structure, with this figure. Now we need to determine the equivalent resistor of this combination of resistors. Now if you'll observe here is that this value of R by 2 is in parallel with this value of resistor R. Okay, since the endpoints of both these resistors are common. Okay, so what we can do is we can use the formula for parallel combination of resistor to determine the equivalent value of the resistor between these 2 points. Okay, so when we'll be using the equivalent resistor formula for parallel case, okay, since there are two resistors R1 and R2, after rearranging it, we can get R equivalent as R1 R2 times divided by the summation of the resistors. Okay, now in this case R1 is R by 2. Okay. The other resistor R2 is R. Okay, so R divided by the summation of these two resistors. Okay. So after solving it, what we'll be getting is R equivalent as R divided by 3. Okay, so this is the value of resistor, okay, which is the result of the parallel combination of these two resistors. Okay, so what we can do now is we can replace these two resistors by a single resistor of value R by 3. Okay, so we will remove these two resistors and replace it by a single resistor whose value is R by 3. Okay, now this simple is now it's simple. We can see from here is that in this circuit, okay, now we are left with two resistors R and R by 3 which are connected in series, since the current in both these branches are same. Okay, so they are said to be in series. So after applying the formula for series resistors, when the resistors are connected in series, okay, we'll call this resistor as R1, this as R2. Okay, so we'll be getting it as R1 is same as R, and the other value of resistor R3, okay, this is equal to R2 is equal to R divided by 3. Okay, so here the equivalent resistor for these two resistors would be 4R by 3. Okay, so here what we can do is we can replace these two resistors by a single resistor of value 4R by 3. Okay, so we can remove this branch and introduce another branch whose value the resistor is 4R by 3. Okay, now at the end we are left with two resistors, and as we can see both these resistors have their ends in common, so that means that these two resistors are again in parallel. So again we'll be using this formula for equivalent resistance for the parallel case to determine the equivalent combination between the points A and C. Okay, So if we'll be using this formula, what we'll be getting is the parallel result, the parallel combination result for these two resistors. So this is R1 R2 times R1 plus R2. Okay, so R1 is 4R by 3 times R2, the other resistor whose value is R, divided by the summation of these two resistors. So it would be 4R by 3 plus R. Okay. So by solving it, we'll be getting it as 4R by 7. Okay. So the final resistor between the points A and C, okay, is a single resistor of value 4R by 7. Okay. So we can, at the end, we can replace the complex circuitry by a single circuit whose resistor, single conductor whose resistor is 4R by 7. Okay. Now, but this is just half of the problem solved. Okay, because we also have the other symmetrical plane. But now, since the circuit was symmetrical, the other half would also be giving us the same result of 4R by 7 between the points C and B. Okay. So what we can do is now we can connect that part of the resistor 4R by 7 in series with this point. Okay. So we have the other resistor 4R by 7 which is in series with this resistor. Okay. Okay. So now we want to find the value of the equivalent resistance between the points A and B. Okay. Now since these two resistors are in series, the equivalent resistor between the points A and B would be the summation of these two resistors. So at the end, RAB would be the summation of 4R by 7 plus 4R by 7. Okay. That means, implies that the equivalent combination for the resistors of the original problem is 8 times R by 7. Okay. So this is the value of the equivalent resistance which we can see for the original problem. Okay. So this is how we can say that even though the circuit was not in the initial stages, it was not neither in series nor in parallel, but after some modifications, as in this case for the symmetrical plane, we got the resistors in the combinations for series and parallel. Okay. So in this manner, we can reduce any complex circuitry into very simple circuitry containing series and parallel combinations for resistors.